Welcome to the next lecture series in frequency response analysis. We discuss the starting point from transfer function, and then we move to body plots, and now in this particular lecture we are going to focus on resonance condition. So resonance condition we are going to discuss in two different parts. So this is the first part, and then we will have the second part. So let us see the introduction first. We have seen that in the frequency response, in the magnitude response, the special feature will be there, that is the sharp peak will be there, which is known as the resonant peak, and it is exhibited only in the amplitude characteristic. So frequency response will have the magnitude as well as the phase. The magnitude, which is the amplitude characteristic, one special feature is there, which is the sharp peak in the frequency response. That peak is basically known as the resonant peak. Now, what is resonance and what is the spatial importance of these resonant peaks that we are going to discuss. So these resonant peaks are generally occurring in the systems or the circuit where the complex conjugate pair of poles are there. So poles being in the complex conjugate, and they are the reason for the oscillations of stored energy from one form to another. So we know that the energy storage element inductor and the capacitor which is present in the network, there will be a continuous flow of the energy between the electric field and the magnetic field, and due to the presence of these complex conjugate pair of poles, the oscillations will be there, and due to the oscillation there will be a result of the resonant peak. Generally, in communication network, we required to discriminate the frequency so that we eliminate some frequency and take some other frequency component. So we should have at least one inductor and one capacitor in combination to get a circuit which is known as the resonant circuit. So at least one inductor and one capacitor should be present in the network. Now, if I define what is resonance, so the definition goes like this, that whenever we are taking the RLC circuit, there is one condition which is occurring in the RLC circuit where the capacitive reactance and inductive reactance will be equal. And we know that the net impedance of any RLC network will be equal to the resistive part, which is the real part, and then we will have the imaginary part, which is XL minus XC. And now we can take the mod of this so that because we don't know whether XL is greater than XC or XC is greater than XL. Now this is the impedance, which is a complex quantity. Now, if there is one condition occurring where XL and XC are equal, then in that case, the net impedance of the network, the magnitude, is equal to the resistance, which is purely resistive network or purely resistive impedance. Such type of condition is known as the resonance condition, and the circuit is known as the resonant circuit. So resonant circuit can be in the form of a series RLC network, or it can be in the form of parallel RLC network. They are generally used in the construction of filters because the transfer function which are used for obtaining the frequency response can be highly frequency selective. So RLC resonant circuit can be series resonant circuit and parallel resonant circuit, and in the field of communication network we required filters, and these filters are basically frequency selective network. So the filters will be used in different applications like radio as well as the TV receivers. So those are related to the communication networks. So the resonant circuit, which are divided into two circuit, that is the series resonance and the parallel resonance circuit. And in this particular lecture, we will focus on series resonance, and in the next lecture, we are going to focus on parallel resonance. So we have a series RLC network where the resistor, inductor and capacitor are connected in series. So the current which is flowing in the network due to the source is AC. In that case, the same current will be flowing through the resistor, inductor and capacitor because they are in series. If we obtain the transfer function h of omega in the form of impedance Z, which is the ratio of the supply voltage Vs by the source current I, that is in phasor form, then we can write that in the form of the impedance equation, which is R plus j omega L plus 1 by j omega C. Now these impedance equation we can obtain in a much better form, where the real part is the resistance and the imaginary part is omega L minus omega C. The imaginary part of Z, which is omega L minus omega C, if we equate to 0, this is the resonance condition. So there will be one frequency omega naught, which is known as the resonant frequency, at which the impedance of the circuit will be purely real or resistive. So the Z will be equal to R, which is purely resistive network, and the frequency is known as the resonant frequency. So the condition of inductive reactance is equal to capacitive reactance. We can say that at the resonant frequency omega naught, we can write omega naught L, which is the inductive reactance. Capacitive reactance is 1 by omega naught C. Now from these relationship, we can obtain the omega naught value, which is 1 by under root of LC, and the unit is in radian per second. So this is the first equation to be remembered, which is the resonant frequency, which is equal to 1 by under root of LC for any network. So given the inductor and the capacitor value, we can obtain the resonant frequency of the network, which is 1 by under root LC. Now this is in radian per second. If I need to obtain in hertz, the value f0, that is the resonant frequency in hertz, is 1 by 2 pi under root LC. So sometime we need to obtain in radian per second and sometime we need to obtain in hertz. So we can use these equations to solve the problems. Now we have understood the resonant frequency in radian per second, the resonant frequency in hertz, and the series RLC network. So the important points to be noted at the resonance condition is that the impedance will be equal to the resistance, and it is purely resistive in network. It means that the series combination of the inductor and the capacitor acts as a short circuit, and the entire voltage of the source is across the resistance. So all the voltage will be across the resistance, and the inductor capacitor combination, which is in series, will act as a short circuit. Next point is that the source voltage Vs and the source current Is, since it is flowing through the resistance and inductor and capacitor is short circuit, we can say that the voltage and current are in phase because the circuit is resistive in nature. So the power factor is unity because the phase angle, that is the angle between the voltage and the current, will be equal to 0, and we know that cos phi will be equal to 1, and that is known as the power factor. So power factor will be unity under the condition of resonance, and if we obtain the impedance value, that will be minimum. So the transfer function or the impedance will be minimum, which is equal to the resistance. Now what happened to the inductor voltage and the capacitor voltage at the resonance condition? So inductor voltage and capacitor voltage will be much more greater than the supply voltage Vs. How it is? We know that the voltage across the inductor VL is equal to the current multiplied with the inductive reactance XL, and XL we know that it is equal to omega L. So if I substitute the current which is flowing in the network is equal to the value of Vm by R, because the circuit is entirely resistive in nature, so I get the magnitude of VL is equal to Vm by R omega naught L. So at the resonance frequency omega naught is given. So the value of omega naught L by R, these we can put it as Q into this quantity Vm. So we can say that if Q is a positive quantity, Q is greater than 0, positive quantity, obviously we will say that VL is greater than Vm. So if the Q value is very high, the VL will be very high. Similarly, for VC derivation, we can do it. So the capacitor voltage is equal to current multiplied with the capacitive reactance XC, and XC is equal to 1 by omega C. So at the resonant frequency, we can write it is equal to Q into Vm, where Q is defined as the quality factor, which we are going to define a little moment later. So the quality factor of the circuit given from the inductance and the capacitance, we are going to see that will make the inductor voltage and capacitor voltage much greater than the source voltage Vs under the condition of resonance. So if we obtain the series RLC network, so we have a series RLC network, the source voltage Vs at the condition of resonance, we can obtain 0 volt across the LC combination. So if we see the LC combination, 0 volt is there, and entire voltage, source voltage will be occurring across the resistor, and the current and voltage will be in phase. So the current I and the source voltage Vs will be in phase, and the inductor voltage VL and the capacitor voltage VC will cancel out each other in opposite direction, and the value of Vs and Vr will be equal. So as we see that the under the resonance condition, the voltage we are talking about, so it is the voltage resonant circuit, mostly known as the series resonant circuit. So series resonant circuit are otherwise known as voltage resonant circuit. If we draw the waveform of different quantities like the current, source current versus the frequency, we can say that the current will be maximum at the resonant frequency. So when the frequency is at the resonant condition, then the current is maximum, and the maximum current which is flowing in the network is Vs by R. If we draw the resistive voltage Vr with respect to the frequency f, we say that this is the resonant frequency. So at the resonant frequency, our Vs and Vr will be equal. Not before that, not after that. So at the resonant condition, Vs and Vr will be equal. Whereas if we talk about the capacitor voltage or the inductor voltage, at the resonant condition, it will be much more greater than Vs. So we can see that the Vc is much more than the supply voltage. Similarly, the inductor voltage VL is much more than the supply voltage. Whereas if we take the series combination of the inductor and capacitor, at the resonant condition, that will be equal to 0 volt, because it is under short circuit condition. So that is the phenomena which is going on in the series RLC network under the resonant condition. If we further draw the waveform of the impedance Z with respect to the frequency on the x-axis, then we know that XL, which is the inductive reactance, is equal to omega L. It means that XL is directly proportional to omega, and XC, which is equal to 1 by omega C, it means XC is inversely proportional to omega. So that will decide the waveform of inductive reactance and capacitive reactance. So we can say that the inductive reactance XL is a straight line passing through the origin, and it is linear because it is directly proportional to the frequency on the x-axis. Since Xc is inversely proportional to frequency, so it will be a falling exponential graph, which is Xc. Now at the condition of the resonance Fr, we know that if we draw the impedance graph, we will be getting the minimum point at the resonant frequency. So the impedance graph will have the minimum point, which is Z is equal to R, and the power factor graph, if we draw, it will be under the unity power factor condition. So this is the power factor curve, this is the impedance curve. So power factor will be unity under the condition of the resonant frequency, and the impedance will be minimum, which is equal to the resistance, current will be maximum, and below the resistive below the resonant frequency, the circuit will be leading in nature, and above the resonant frequency, the circuit will be lagging in nature. When the circuit is lagging, when XL is more than XC. Leading in nature is means XC is more than XL. So the circuit will be divided into two different parts under the condition of resonant frequency. So the important point to be remembered here is that under the resonance, the impedance will be minimum, which is equal to the resistance. The power factor will be unity. That is the two important factor points that need to be remembered. Now let us talk about the current. So current magnitude is the voltage Vm divided by the net impedance of the network. This is the current which is flowing. Now the average power which is dissipated is half I square R. This we have discussed in detail when we were discussing the AC network, how the average power is calculated. So maximum power dissipated in the network will be half Vm square by R, because we know that the current is equal to Vm by R. So if I draw the current waveform with respect to the frequency, then at the resonant frequency omega naught, the current is maximum, which is equal to Vm by R. Now we are going to talk about the two different frequency component, omega 1 and omega 2, which is known as the half power frequency, because at this frequency the power will be half the maximum value. So the maximum power, that is half Vm square by R, if we do the half of that, that will be occurred at the frequency omega 1 and omega 2, which is known as the half power frequency. So the power at omega 1 and omega 2, which is equal and half power frequency, if we say, then the maximum power is Vm square by 2R. So half of that if we obtain, then we will get Vm square by 4R. Now what happened is that if we set the denominator of the current here, which is under root R square plus omega L minus 1 by omega C square, is equal to root 2 times R, because we can say that the denominator will be root 2 times R under the half power frequency. Then in that case we can find the frequency omega 1 and omega 2, which are the half power frequency given by this relationship. So if we see the relationship, the first part is minus R by 2L, then we have a plus sign under root R by 2L square plus 1 by under root LC. So this is the value of omega 1. Omega 2, you do not have a negative sign here, so this is R by 2L plus the same component whatever we have in the omega 1 term. So omega 2 is this, and omega 1 and omega 2 both are equal. This relationship is only for series RLC network. Same derivation we are going to do when we will be talking about the parallel RLC network. Now, the resonant frequency omega naught is basically the geometric mean of the half power frequency. So half power frequency omega 1 and omega 2, we can obtain the omega naught as the geometric mean of omega 1 and omega 2. Note here that omega 1, omega 2, that is the half power frequency, are not symmetrical around omega naught. So if you see omega naught here, which is the central point where the power factor is unity and the resonance condition is occurring, omega 1 on the left and omega 2 on the right are not symmetrical because the frequency response itself is not symmetrical. However, it is often a reasonable approximation can be obtained. Now, the height of the curve, if we take the resonant curve, the height is basically determined by the resistance, whereas the width is determined by the bandwidth. So what is this bandwidth, which is a very important term? Bandwidth is basically the difference between the omega 2 and omega 1. So omega 2 is the half power frequency, which is on the right hand side of omega naught, whereas omega 1 is the half power frequency on the left hand of omega naught. Then bandwidth is the difference of omega 2 minus omega 1. This bandwidth plays a very important role in the communication network. We will introduce one new term, that is the quality factor, which we have taken previously, and we have seen that the inductor voltage and the capacitor voltage at the resonance condition is quality factor times the source voltage Vs. Quality factor is basically quantity measurement of the sharpness of the resonant in the resonant circuit. So we have seen that in the resonant circuit there will be some sharpness. This is the sharpness curve. So quality factor is that measurement, which is defined as quality factor is equal to 2 pi times peak energy stored in the circuit by energy dissipated by the circuit in one period at the resonance condition. So this is the definition of the quality factor. We will do some derivation on the quality factor and understand its importance. So it is basically quantitative measurement of what? The sharpness of the resonance condition, and bandwidth is the difference of the two frequency omega 2 minus omega naught 1, and omega naught is the resonance condition, which is the geometric mean of omega 1 and omega 2. So quality factor in easy term, if we define, that is energy stored by energy dissipated. Energy stored in the reactive power, whereas energy dissipated will be the true or active power. Reactive power is I square XL, whereas the true power is I square R. It means that the ratio will give me XL by R. So the relationship we are getting, that quality factor is equal to XL by R, where XL is the inductive reactance of the network and it is coming from the power relationship. Now, if I put the value of XL as omega naught into L, then we are getting omega naught into L by R as the quality factor. Otherwise, in terms of the capacitance, we know that XL is equal to XC under the resonance condition, and Xc is equal to 1 by omega C, and under the resonance condition we are going to put omega naught. So that will give me a relationship 1 by omega naught Rc, that is the quality factor of the network. So in general we can say that quality factor is equal to XL, that is the inductive reactance, or Xc divided by R. Either we can go from the inductive reactance side, or we can go from the capacitive reactance side. And the bandwidth, which is, we have defined that the bandwidth is omega 2 minus omega 1, that is the half power frequency on the RHS of the omega naught, that is the resonance frequency, minus the left hand side of the cutoff frequency omega 1. So bandwidth is basically given by R by L, which is equal to omega naught by Q, that is the quality factor of the network. Because from these relationship, if I want the bandwidth, so the bandwidth is equal to R by L, and this R by L if we take, then we'll get omega naught by Q. On the other hand side, if we take from omega naught RC, then we'll get omega naught square into RC. So once we have got the quality factor, we can determine the bandwidth also. So this is what we are talking about, the sharpness of the curve, and we are going to understand how the sharpness of the curve is related with the quality factor. First thing that to be noted here is that the quality factor of the resonant circuit, if it is high, the bandwidth will be low. Let us see how it is. So a curve of greater selectivity we have taken. If we see the bandwidth is less. So if the bandwidth is less, obviously the quality factor will be more and the circuit will be greater selectivity in nature. Whereas lower selectivity curve, if we say, the bandwidth will be more. So here the bandwidth will be more for the lower selectivity network. Generally in communication network, we go for greater selectivity network. So quality factor of a resonant circuit, if we define it, we can define from the energy stored by energy dissipated, or we can define as the ratio of the resonant frequency by bandwidth. And the selectivity that we are talking about here, the greater selectivity, lower selectivity, if we define it, what is selectivity of the RLC network? It is the ability to respond to a certain frequency and discriminate against other frequencies. For example, if we take one waveform and we take the frequency F1 here, if you want to pass this frequency and eliminate this frequency, that is known as the selectivity. So in the selectivity, we are trying to determine the ability to respond to certain frequency component. Like this frequency we are taking and this frequency we are discriminating. And that is what we are doing in the communication network. So if the quality factor must be high for the frequency band to be selected or rejected. If you want to select the frequency or reject the frequency, we need the quality factor of the circuit must be high. On the other hand, if the band of frequency is wide, this was narrow. If the band of frequency is wide, quality factor must be low, which is we can see from the bandwidth also. Like for the greater selectivity network, if we see the bandwidth, it is narrow. What we are getting? We are getting the frequency band narrow, and the lower selectivity, we are getting the bandwidth to be wide. So the quality factor must be high under the narrow condition and quality factor must be low under the wide condition. Generally in communication network, we use high Q circuit, means high quality factor circuit, where Q is greater than equal to 10. For all practical purpose, the easy way to calculate omega 1 and omega 2, that is the half power frequency, about omega naught is omega naught minus b by 2, that is half of the bandwidth will get omega 1, and omega naught plus half of the bandwidth will get omega 2, because our response is like this. So this is omega naught, which is the resonant frequency. Omega 1 is here, which is on the LHS side, left hand side, and omega 2 is on the right hand side. So if this is total bandwidth, then half bandwidth if we subtract from omega naught, we will get omega 1. Half bandwidth if we add in omega naught, we'll get omega 2. Although we are taking it to be approximate solution, not the exact solution, because the circuit is not symmetrical. What the frequency response we are getting is not symmetrical. So omega 1 and omega 2 is also not symmetrical. So generally the quality factor greater than 10, which are high quality factor circuit, that are used in the communication network. So generally 5 related parameters are there which define any resonant circuit. What are they? The resonant frequency omega naught, 2 frequency half power frequency omega 1 and omega 2, the quality factor and the bandwidth. These are the 5 related parameters that will be defining any resonant circuit. We will take up one problem to understand the resonance condition of the series RLC network. So given the series RLC network, the values are the resistance is equal to 2 ohm, inductor is 1 millihenry, and capacitor is 0.4 microfarad. Determine the resonant frequency omega naught, the half power frequency omega 1, omega 2, the quality factor Q and the bandwidth B, and the amplitude of the current, that is we need to determine what is the current which is flowing under the condition of resonant frequency and the half power frequency omega 1 and omega 2. So the first we have to obtain the resonant frequency omega naught, which is directly going to come from the circuit itself given by 1 by under root LC, and if we substitute the value of L and C, we will get the omega naught, which is equal to 50 kiloradian per second. Now there are two different methods to solve this problem. We'll go by method 1, where we'll find the half power frequency omega 1 and omega 2 directly from the RLC component, which is equal to minus R by 2L plus under root R by 2L whole square plus 1 by LC. This is the first formula. And here in the second formula, we have the negative sign to be removed. So that gives me 49 kiloradian per second and 51 kiloradian per second. So these are omega 1 and omega 2 half power frequency. Now if I draw that, the waveform, so the omega naught, which is 50 kiloradian per second, the omega 1 we are getting 49 kiloradian per second, and omega 2 we are getting 51 kiloradian per second. So my bandwidth is basically omega 2 minus omega 1, which is 2 kiloradian per second. Or otherwise I can find the bandwidth by the ratio of R by L, which is also giving me the same result, 2 kiloradian per second. Quality factor is nothing but resonant frequency by bandwidth. So resonant frequency is 50 kiloradian per second and the bandwidth is 2 kiloradian per second. It means the quality factor is 25. The second method to obtain the solution is going from the quality factor directly. So omega naught L by R is basically 25, which is the quality factor of the network, and the B value, that is the bandwidth, is omega naught by Q, Once we have got the Q value and omega naught, we'll get B, that is 2 kiloradian per second. So the bandwidth that we are getting from the half power frequency and the quality factor both are same. And then we can obtain the half power frequency omega 1 and omega 2 by adding and subtracting the half bandwidth from the resonant frequency. We will get 49 and 51 again as the same solution. The final thing, we have to determine the current what is flowing in the network at the resonant frequency and the half power frequency. At the resonant frequency, current will be maximum, which is I equal to Vm by R, that gives me 10 ampere, whereas under the half power frequency, the current is Vm by root 2R, because here the power will be half, the current will be divided by under root R. So the impedance of the network that we are going to take is under root 2R. Here we have derived this, we are getting 7.071 ampere, the current flowing at the half power frequency, and 10 ampere is the current which is flowing at the resonant frequency. So in this particular lecture, we have focused our discussion on the introduction of the resonance and the series resonant circuit. In the next lecture, we are going to focus on the parallel resonant circuit. Thank you for now.